Welcome to our quantum deep dive. Today, we're plunging into the absolute core of matter itself, the nucleon. This isn't just about, tiny particles. It's really about the fundamental building blocks of everything you see, touch, and, well, even are.
That's right.
And our guide for this deep dive is going to be insights from the brilliant essay Nucleon Baustein der Materie in der Quantenphysik by Jürgen Schneepapat. I think this is going to reshape how you think about reality.
It really might. Nucleons are the very heart of every single atom, but they conceal these incredibly complex quantum secrets. And what's truly fascinating, I think, is how they bridge that gap between our everyday sort of classical world and the, well, mind-bending quantum realm. As we unpack their properties today, you'll start to see how understanding them is unlocking technologies that could revolutionize, everything from medical imaging to the future of energy and computing.
Okay, all right, so we're talking about the bedrock of matter. Let's get down to brass tacks, though. When we say nucleons, what exactly are we talking about, like at the most basic level?
Well, the term itself, nucleon, it just comes from the Latin word nucleus, which means core. Pretty straightforward. In modern physics, it's basically our shorthand for referring to either a proton or a neutron. Both are subatomic particles, and they belong to a family called baryons, which just means they're made up of three smaller particles called quarks. There are also fermions, which might sound a bit technical, but it's really crucial. It means they have this half-integer spin property.
Spin? Okay.
And that property dictates that no two identical nucleons can occupy the exact same quantum state. It's absolutely foundational to the structure and stability of all matter we see.
Got it. So protons and neutrons. Now, on the surface, they seem, well, pretty similar, but what are those crucial distinguishing factors? What makes them behave so differently?
Yeah, they are distinct, but they're also intimately related. Protons, well, they carry a positive electric charge, while neutrons, as the name suggests, are electrically neutral, zero charge. You find protons in absolutely all atomic nuclei. They give an atom its identity as an element, like carbon is carbon because it has 6 protons. Neutrons are also present in almost all nuclei. The main exception is protium, which is the most common form of hydrogen, just one proton, no neutrons.
Yeah.
Here's where it gets really profound. Despite that charge difference, their masses are incredibly close. A proton is about 938.27 MeV, and a neutron is just slightly heavier, around 939.57 MeV.
Tiny difference.
Tiny. Think about this. That minuscule mass difference, less than 0.25%, it doesn't just influence nuclear reactions, it's like the fundamental lever that dictates the stability of every single atom in the universe.
Wow.
Without that tiny difference, the cosmos as we know it wouldn't exist.
That's a really powerful thought. Okay, so protons and neutrons. But you mentioned something earlier about an inner structure. They're not just tiny, solid little marbles, are they?
Absolutely not. No, this is where the quantum world really starts to defy our everyday intuition. Nucleons are not elementary particles. They have this complex internal structure. Each nucleon is made of 3 primary components called valence quarks.
Valence quarks.
Right. So a proton consists of 2 quarks called up quarks and 1 called a down quark. While a neutron is sort of the opposite, 2 down quarks and 1 up quark.
Up and down quarks. Okay, so it sounds almost chaotic inside there, maybe ephemeral. With these quarks moving around, what's the force that manages to keep all this incredible dynamism bound together inside the nucleon?
That's the strong interaction, or sometimes called the strong nuclear force. It's mediated by particles called gluons.
Gluons, like glue.
Exactly like glue. These gluons are the force carriers. And unlike photons, light particles which don't interact with each other, gluons carry something we call color charge. Now, this is an actual color, obviously. It's a unique quantum property, and it means gluons actually stick to each other.
They interact with themselves. It's different.
Very different. Imagine if light waves just clumped together. It's the self-interaction that makes the strong force so incredibly complex and, well, strong. It binds those quarks together. And beyond these main valence quarks, there's also this dynamic sea of virtual quark-antiquark pairs. They're constantly popping into and out of existence because of quantum fluctuation.
Okay, hold on. Virtual particles popping in and out.
Yeah, it's a consequence of quantum uncertainty. And this isn't just some, interesting side note. It's a profound revelation. The nucleon's total mass is far greater than the sum of the masses of its tiny constituent quarks.
Wait, so where does all that extra mass come from?
Exactly. It means most of the mass of every proton and neutron, and therefore most of the visible mass in the entire universe, comes not from the quarks themselves, but from the sheer energy of these quantum fluctuations and the strong force field binding them together.
So mass from pure energy, like IMC-TAC in action.
Precisely. It's mass from energy embodied in the strong force dynamics.
That's truly astonishing. Okay, so if these quarks are so dynamic and the interaction's so strong, it makes me wonder, can we actually isolate one? Can we ever just see a single quark on its own?
Good question. And the answer is no, you can't. And that's due to a phenomenon called confinement.
Confinement.
Yeah. Imagine trying to stretch a rubber band, but the further you pull it apart, the stronger the force pulling it back gets. You'd never break it, right?
Right, you just snap back harder.
It's a bit like that with quarks. The strong interaction actually increases in strength with distance, so you can't pull a quark out. They're always bound together within particles like nucleons or mesons. However, and here's where it gets really interesting. At very, very high energies, like the kind you get in particle accelerators, the strong interaction actually weakens.
It gets weaker at high energy. That seems counterintuitive.
It does. This effect is known as asymptotic freedom. It means at these extreme energies, the quarks behave almost as if they were free particles inside the nucleon. This was a groundbreaking discovery. It earned David Gross, H. David Pulitzer, and Frank Wilczek the Nobel Prize in Physics back in 2004. It completely changed our understanding of how matter behaves under extreme conditions.
Wow. Nobel Prize stuff. Okay, so given all that quantum chaos and fluctuation you described, I have to ask, how stable are these things? Protons and neutrons, are they just constantly changing, or are they built to last?
Well, their stability is quite distinct. Within the standard model of particle physics, our current best theory-free protons are considered remarkably stable. There's no known mechanism for them to decay. Now, some theoretical ideas, like grand unified theories or GUTs, do propose an extremely slow proton decay, like a half-life exceeding 10 to the power of 34 years, which is just unimaginably long.
Longer than the age of the universe by far.
Way longer, and it's never been observed. So, for all practical purposes, protons are stable. Free neutrons, though, are a different story. They are unstable outside of a nucleus. They undergo beta decay. A neutron transforms into a proton, an electron, and an antineutrino. Its half-life is about 880 seconds.
So about 15 minutes.
Roughly, yeah, 15 minutes. However, and this is key within an atomic nucleus, this decay can be suppressed or modified by the nuclear binding energy. That's why neutrons are stable when they're bound together with protons in most nuclei.
And how do these differences, especially the proton count, influence the atom itself? You said it defines the element.
Exactly. The number of protons in the nucleus is what defines the chemical element. 6 protons, it's carbon, 8, oxygen. Always. That number is fundamental. The number of neutrons, however, defines the isotope of that element. You can have carbon-12, 6 protons, 6 neutrons, or carbon-14, 6 protons, 8 neutrons. Same element, different isotope. And that delicate balance, or sometimes imbalance, between protons and neutrons creates different nucleids, each with its own stability. Stable nuclei tend to have a fairly balanced ratio. If you have too many neutrons or too many protons, the nucleus tends to be unstable and undergoes radioactive decay. This whole interplay is absolutely critical in nuclear reactions, like, the fusion powering stars or the fission in nuclear reactors.
Right, so these complex little packets of quarks and gluons, they're governed by quantum mechanics.
Yeah.
And what's fascinating here is how quantum theory really just radically changes our view of them, makes them seem far from static objects.
Indeed. The fundamental theory describing that strong interaction, the one holding quarks together, is called quantum chromodynamics, or QCD.
QCD.
Right. And it's quite different from, say, quantum electrodynamics, QED, which describes electricity and magnetism. In QED, the force carrier is the photon, and photons don't interact with each other directly. But in QCD, the force carriers are the gluons, and as we mentioned, they carry color charge and do interact with themselves.
That self-interaction.
That self-interaction. It's precisely what makes QCD so much more intricate and, frankly, much harder to calculate, but also much more powerful than QED. It leads to all the complex dynamics we see inside nucleons.
And when you say dynamic systems, not static, what does that really mean for how we should picture them?
It means they're constantly buzzing with activity. Think about the energy time uncertainty principle from quantum mechanics.
Okay, E times that.
Exactly. It basically dictates that for extremely short periods of time, energy can fluctuate quite wildly, and these fluctuations allow for the momentary creation of virtual antiparticle pairs out of the vacuum. So inside a nucleon, the quark-gluon structure isn't fixed. It's constantly boiling with this sea of virtual quarks and gluons popping in and out of existence. Wow.
And these quantum fluctuations aren't just some minor effect. They are crucial. They contribute significantly to the nucleon's overall effective mass, and they even help mediate the residual strong force between nucleons in a nucleus that happens through the exchange of virtual pions, another type of particle.
So it's like the nucleon is constantly throwing a tiny, invisible quantum party inside itself.
That's actually not a bad way to think about it. A very energetic, very strange party.
Okay, so they're not just particles, they also behave like waves. That's the wave-particle duality thing, right? How does that apply here?
Precisely. Wave-particle duality is a cornerstone of quantum mechanics. For nucleons, this wave aspect is described by the de Broglie wavelength. It's basically Planck's constant divided by the nucleon's momentum. Now, because nucleons have a relatively large mass compared to, say, electrons, their de Broglie wavelength is quite short.
So they don't seem very wavy in everyday life. Not usually, no. But this wave property is absolutely essential for understanding certain experimental techniques. Things like neutron scattering, which uses the wave nature of neutrons to probe the structure of materials, and also electron scattering experiments off protons. Those were absolutely key in confirming that protons have an internal structure made of quarks. These experiments let us effectively see inside the nucleon by using the wave properties of particles.
Right, they give us incredibly detailed insights. So what does this all mean for their quantum identity? How do physicists categorize and describe them beyond just mass and charge? Are there other key quantum numbers?
Yes, absolutely. They have fundamental quantum properties that dictate their behavior. One we already mentioned is spin. For a nucleon, it's spin equal half-inch.
They have integer spin.
Right. And this intrinsic angular momentum gives rise to specific magnetic moments, like tiny internal magnets. The proton's magnetic moment is about 2.79 nuclear magnetons, while the neutron's is actually negative, about 1.91 nuclear magnetons.
Negative, even though it's neutral overall.
Yes, because its internal charged quarks are moving. And this intrinsic magnetic property is exactly what allows technologies like nuclear magnetic resonance, or NMR, to work.
Ah, okay. NMR relies on that magnetic moment.
It does. Besides spin, nucleons also possess another interesting quantum property called isospin.
Isospin, like isotope spin.
Not quite. Think of it more like a quantum label. It helps physicists understand an underlying symmetry of the strong interaction. The strong force treats protons and neutrons almost identically despite their charge difference. Isospin helps mathematically capture that symmetry, effectively treating them as different states of the same particle under the strong force. It's incredibly useful for predicting how nuclear reactions will proceed.
Fascinating. And how do these complex little packets interact within the nucleus itself? What actually keeps them all bound together, especially when you have all those positively charged protons trying to repel each other?
That's the job of what's called the residual strong interaction. It's sort of a leftover effect of the super strong force inside the nucleons.
A residual force.
Yeah. This force between nucleons is mediated by the exchange of other particles called mesons. Think of them as tiny quantum messengers flitting back and forth. The most important ones are pions. And unlike long-range forces like gravity or electromagnetism, this residual strong force is very short-range. It drops off incredibly quickly with distance.
Ah, so it only acts inside the nucleus.
Exactly. That's why it holds the nucleus together so tightly, but doesn't really affect electrons orbiting far away or other atoms. It makes atomic nuclei incredibly dense and stable, and it's the force behind the immense energy released in nuclear fusion and fission.
Okay, this is where it gets really exciting for me. How do these tiny quantum building blocks translate into actual technology? Stuff that impacts our lives right now.
Well, one of the most widespread and truly impactful applications is nuclear magnetic resonance, NMR. This technology cleverly uses those magnetic moments of nucleon spins we talked about.
Right, the tiny magnets.
Exactly. When you put atoms in a strong external magnetic field, these nucleon spins start to precess like tiny wobbling tops at a specific frequency. We call it the Larmor frequency. Then we hit them with radio frequency waves tuned to that frequency. This excites the spins. When they relax back down, they emit energy, and by detecting that energy, we can learn an incredible amount about the chemical environment of those atoms, what they're bonded to, their structure.
So wait. Does this magnetic moment thing play a role in technologies we might already know, like medical imaging?
Absolutely. You've hit it. That's exactly how your MRI scan works. Magnetic resonance imaging.
MRI is NMR.
MRI is basically a sophisticated application of NMR principles tailored for medical imaging. It provides these incredibly high-resolution pictures of biological tissues, organs, muscles, brain, all without using any harmful ionizing radiation like X-rays. It has completely revolutionized medical diagnostics, letting doctors see inside the body in stunning, non-invasive detail. And beyond medicine, NMR is indispensable in material sciences for analyzing chemical bonds, molecular structures. Think polymers, superconductors, new materials. Chemists and biologists use it constantly to figure out the 3D structures of complex molecules, especially proteins.
Okay, so MRI is huge. Moving beyond established tech, what about the really cutting-edge stuff, like quantum computing? How on earth can these tiny nucleons become qubits, the bits of a quantum computer?
Well, Nucleon spins are actually seen as really promising candidates for qubits.
Why them specifically?
Their secret weapon, if you like, is their incredibly long coherence times.
Coherence times, meaning?
Meaning they can hold on to their delicate quantum state, the quantum information, for a relatively long time without being easily disturbed by noise or interference from their environment. Decoherence is a huge enemy of quantum computing, and nuclear spins are naturally quite robust against it.
So they're stable information carriers. How do you control them?
We can manipulate these spins using very precisely timed electromagnetic pulses, radio waves again, essentially. These pulses can flip the spins or put them into superposition states, effectively creating the logical gates needed for quantum circuits.
Are there downsides?
Well, yes. While they're robust, they're generally harder and slower to manipulate than some other types of qubits, like superconducting circuits or trapped ions. Scalability is also a challenge, controlling thousands or millions of them precisely, but their long coherence is a massive plus. So a lot of research is focused on improving control, maybe using them in hybrid quantum computers that combine the strengths of nuclear spins with other faster platforms.
Hybrid approaches? Interesting. What about quantum sensing? Can nucleons help us make incredibly precise measurements?
Yes, definitely. Those same properties, their stable spin and magnetic moment, make Nucleon spins extremely sensitive probes. Basically tiny quantum sensors. By precisely measuring how these spins precess or react to their environment, we can detect minute variations in magnetic fields, electric fields, even potentially gravitational fields, far beyond what conventional sensors can achieve.
Like what kind of applications?
One key example is ultra-precise atomic clocks. Many of the best atomic clocks in the world rely on measuring transitions related to nuclear spin states within atoms, specifically the hyperfine structure. The precision is just staggering.
How precise?
We're talking timekeeping accurate to parts in 10 to the 18 or even better. That's like losing or gaining less than 1 second over the entire age of the universe.
It's hard to even comprehend. What else could you do with that kind of sensitivity?
Well, for navigation, think about highly precise quantum sensors based on nuclear spins. They could potentially lead to GPS-independent navigation systems.
No GPS needed.
Exactly. Systems that work deep underground, underwater, inside buildings, anywhere GPS signals can't reach. Maybe even for deep space missions. Imagine navigation perfect down to the millimeter, totally independent of satellites. That's the long-term vision.
Wow.
And in material research, these sensors let us probe material properties at the atomic scale, measuring local magnetic fields, looking for tiny defects, or performing incredibly refined NMR structural analysis. They could even be used to search for exotic new physical effects or tiny deviations from the standard model of particle physics.
It's incredible how much we've learned. But how do scientists actually see these things? Or I guess, infer their behavior, probe their insides? And what's next? What's on the horizon for Nucleon research?
Right, we can't see them with light like everyday objects. To probe the internal structure, we mainly rely on high-energy experiments using particle accelerators. Places like the Large Hadron Collider at CERN or the Relativistic Heavy Ion Collider in the US.
How do those work? Smashing things together.
Pretty much. We accelerate protons, or sometimes heavier ions like gold or lead nuclei, to near the speed of light. They gain enormous energy. Remember Einstein's E equals bumsic?
Right, mass energy equivalence, boosted by the relativistic gamma factor.
Exactly. Then we collide them head-on. The immense energy released in these collisions allows us to create showers of new particles and, crucially, to probe the interactions between the quarks and gluons inside the colliding nucleons. It gives us deep insights into the strong force and lets us test the predictions of QCD with incredible precision.
And at those extreme energies, you can create some really exotic states of matter, right?
Yeah.
You mentioned something like conditions just after the Big Bang. The quark-gluon plasma.
Absolutely. If you collide heavy ions with enough energy, the protons and neutrons essentially melt.
Melt.
Yeah, they transition into this exotic state of matter called the quark-gluon plasma, or QGP. This is believed to be the state of the universe just microseconds after the Big Bang, a phase where quarks and gluons aren't confined inside nucleons anymore, but exist as sort of a hot, dense, free soup.
A primordial soup. How do you know you've made it?
We look for specific signatures. Things like jet suppression, where high-energy jets of particles created in the collision lose energy as they plow through this dense plasma. Or J suppression, where the plasma makes it harder for certain heavy quark pairs, like charm and anti-charm, to bind together into particles called J mesons. Studying this QGP helps us understand QCD under extreme conditions and, test our theories about the very early universe.
Fascinating. What about neutrinos? They're famous for being elusive, the ghost particles, but they interact with nucleons too, don't they?
They do, though very rarely. Neutrinos interact primarily through the weak nuclear force, which is, much weaker than the strong or electromagnetic forces. They're almost massless and electrically neutral, so they mostly just fly straight through matter. Detecting them is a huge challenge.
How do they interact when they actually hit something?
It happens via processes mediated by W or Z bosons, the carriers of the weak force. A neutrino might just bounce off a nucleon that's called elastic scattering. Or, in a charged current interaction, a neutrino might hit a neutron, turn it into a proton, and produce an electron or muon in the process. That's quasi-elastic scattering. Because these events are so rare, we need absolutely massive detectors, often built deep underground or under Antarctic ice to shield them from other cosmic rays. Think of experiments like Super Kamiokande in Japan or IceCube at the South Pole.
And what's the payoff for building these enormous, difficult experiments? What do neutrino interactions tell us?
They provide crucial insights into the weak interaction itself, and they're a key testing ground for the Standard Model. If we see deviations from the predicted interaction rates or types, it could be a huge sign of new physics beyond the Standard Model. People are looking for things like sterile neutrinos, hypothetical neutrinos that don't even feel the weak force, or a process called neutrinoless double beta decay.
What would that mean?
If observed, it would prove that neutrinos are their own antiparticles, which would have profound implications for our understanding of fundamental symmetries and maybe even why there's more matter than antimatter in the universe.
Wow, big questions. Okay, switching gears slightly to something that could genuinely transform our energy future. Nuclear fusion. How do nucleons fit into that picture?
Nuclear fusion is essentially the process of merging light nucleons nuclei to form a heavier one, releasing a tremendous amount of energy in the process. It's the power source of stars, including our sun.
Like hydrogen fusing into helium.
Exactly. A common reaction pursued for fusion power on Earth involves fusing deuterium, 1 proton, 1 neutron, with tritium, 1 proton, 2 neutrons. They combine to form a helium-4 nucleus, 2 protons, 2 neutrons, plus a free neutron, and release about 17.6 MeV of energy. That energy comes directly from the mass difference, again via EMCF4.
Sounds great. What's the catch? Why don't we have fusion reactors everywhere?
The main challenge is overcoming the Coulomb barrier. Protons are positively charged, so they strongly repel each other electromagnetically. To get them close enough to fuse via the short-range strong force, you need incredibly high temperatures, millions of degrees and high densities, like in the core of a star. Recreating and containing that on Earth is extremely difficult.
Right, but isn't there a quantum trick involved? Something about tunneling.
Ah, yes. Quantum mechanics provides a crucial helping hand here. Quantum tunneling.
Like a cheat code.
Kind of. Classically, if two protons don't have enough energy to climb over the top of that repulsive Coulomb hill, they should just bounce off each other. But in the quantum world, there's a small but non-zero probability that they can just sort of tunnel right through the barrier, even if they don't have enough energy to go over it.
They just appear on the other side.
Effectively, yes. This quantum tunneling allows fusion to happen at temperatures significantly lower than classical physics would predict, though still incredibly hot by our standards. Understanding and modeling this tunneling, along with sophisticated techniques for heating and magnetically confining the hot plasma fuel in devices like tokamaks and stellarators, are key areas where quantum physics directly informs our progress towards sustainable fusion power.
Okay, this raises a really important question then. What are the big mysteries left about nucleons?
Yeah.
What don't we understand? And how might all this quantum tech we've discussed actually help unravel them?
Oh, Despite everything we've learned, many fundamental questions still remain. Probably the biggest is the mass mystery we touched on earlier.
Why they weigh so much more than their quarks.
Exactly. We know the quark-gluon dynamics, the energy in the strong force field, contributes most of the mass. But calculating that precisely from first principles in QCD is incredibly challenging due to the complexity of the strong force. We have good approximations, but a full understanding is still elusive. Then there's the question of substructure. Is there anything inside quarks and gluons? Are nucleons the end of the line? Or is there an even deeper layer of reality? Some theoretical models propose substructure, like prions, but there's currently no experimental evidence. And of course, the profound question of proton stability we mentioned, are they truly forever stable? Or do they decay on timescales far longer than the age of the universe? As predicted by some grand unified theories, detecting such a rare decay would be revolutionary.
So how might quantum computing help tackle these enormous theoretical challenges? You mentioned QCD simulations.
Yeah, right. Quantum computers hold immense promise here. Simulating QCD accurately is just brutally difficult for classical supercomputers because of the complexity and the quantum nature of the problem. But quantum computers are naturally suited to simulating quantum systems, using quantum algorithms specifically designed for things like lattice QCD, where space-time is modeled as a grid. We could potentially perform much more accurate and realistic calculations of Nucleon structure and properties.
What could that tell us?
It could potentially give us a definitive answer to the mass mystery, allow us to calculate Nucleon properties like spin and magnetic moment from scratch, maybe even predict the existence of exotic particles or new states of nuclear matter. Beyond computation, new theoretical frameworks are also being developed, things like effective field theories, holographic QCD inspired by string theory, or extensions to the standard model like supersymmetry. These might reveal entirely new ways nucleons interact, or new fundamental principles at play.
And could better understanding nucleons lead to new materials or maybe even new communication technologies?
Absolutely. The field of spintronics currently focuses mostly on electron spins, but imagine current spintronic using nuclear spins to store and process information.
Nuclear spin electronics.
Sort of. If we can precisely control nuclear spins on a large scale, it could lead to entirely new types of materials. Think about hyperpolarized materials, where most nuclear spins are aligned, making them incredibly sensitive for MRI or quantum sensing, or new quantum magnetic materials designed to have extremely long coherence times, which would be a huge boost for building stable quantum computers.
Any communication.
For quantum communication, the robustness of nuclear spins against environmental noise makes them attractive. Their resonant states could potentially act as extremely stable carriers of quantum information. You could imagine nuclear spin qubits being used in quantum repeaters to extend the range of quantum networks, or for highly secure quantum cryptography based on entanglement between nuclear spins. It could form the basis for a future, truly secure global quantum internet.
That sounds incredible. So what are the biggest experimental hurdles we need to overcome to push this research forward, to really unlock these mysteries and technologies?
It really boils down to precision on multiple fronts. We need even higher precision in our experiments to test QCD predictions more stringently and search for tiny deviations that might signal new physics. This means developing even more sensitive detectors and techniques for nuclear spin spectroscopy. It also means building next-generation particle accelerators. There's a major project planned in the U.S. called the Electron-Ion Collider, or EIC.
EIC, what would that do?
It's designed specifically to collide electrons with protons and nuclei at high energies with unprecedented precision. It would act like a super-resolution microscope for looking inside the nucleon, mapping out the quark and gluon distributions, understanding how mass and spin arise from them in much greater detail than ever before. We also need continued advancements in quantum optical methods using lasers and other techniques to manipulate and measure individual nuclear spins with incredible accuracy. The synergy between particle physics, nuclear physics, quantum optics, and quantum information science is really driving progress here. The next few decades promise to be truly revolutionary in our quest to understand the nucleon.
What an absolutely incredible journey through the quantum world of the nucleon. We went from their basic definition as protons and neutrons to their, mind-bending internal structure of quarks and gluons, and then seeing their pivotal role in everything from MRI scans that see inside us to the future of quantum computing and maybe even clean fusion energy. It really hits home that these tiny quantum building blocks truly underpin so much of our universe and potentially our future innovations.
It's true. The Nucleon really exemplifies how digging into the most fundamental aspects of reality, even things that seem incredibly abstract and remote, can lead to these profound insights and truly transformative technologies that shape our world from medicine to materials to energy. The ongoing research into their remaining mysteries and the development of new quantum technologies leveraging their unique properties will absolutely continue to push the boundaries of what we thought possible. It just reminds us, doesn't it, that sometimes the smallest particles hold the very biggest secrets.
A perfect thought to end on. Thank you so much for joining us in this deep dive into the Nucleon. And remember, for more fascinating insights into quantum physics and the work of Yurgo Schneepat, you can always explore schneepat.de. Until next time.